Hey everyone, Cas van Cote here. Thank you for tuning into this video recording about Nimplant made for Black Hat Arsenal 2024. In this recording, I will briefly discuss what Nimplant is, go a little bit over the design, but mostly just demo it and show what it's all about. So let's get into that. First of all, let's start with a quick introduction. My name is Cas van Cote. As I mentioned, I'm based in the Netherlands, and by trade, I'm a red team operator. But mostly, I like to build tools, offensive security tools specifically in modern languages. So I call myself a malware linguist for that reason. I don't like to meddle that much with C, C++, or all those low-level ancient languages. But I do like to meddle with building both malware and other tools to support offensive security operations. And I'd like to do so in the modern languages, as I mentioned. It started out with Nim, which is also the trigger for Nimplant, as we will discuss later. But I also like other modern languages such as Rust and Go. Each have their advantages, of course. I think Rust and Nim specifically are very suitable for low-level development, but I think all three are really enjoyable to use and have their place in offensive security development. So if you're interested in that type of stuff, do reach out. On the right, you can see a little bit my social media handles. I'm mostly active on Twitter, so you can catch me there. But I also try to maintain my GitHub with various repositories and tools that are useful in the context of offensive security development. So if you're interested again, just reach out, or if you will be at Black Hat 2024 in person, of course, find me at the Nimplant booth at the Arsenal. So that's enough about me. Let's talk about Nimplant. Nimplant is a lightweight first stage C2 implant, as I call it. There's a couple of components there, so let's try to break it down. First of all, in its core, it's a C2 implant, right? A command and control implant. For those that are not familiar with the term, that essentially means that it's a tool for offensive security operators to control hosts that they infected or they took over remotely. So that means that, for example, if you do an engagement and you phish a target, of course you want to take over their machine and you want to maintain that control to fulfill the goals of your engagement, whatever those may be. And that's what a C2 implant is for. There are a lot out there already. We will go into that a bit later. But Nimplant specifically focuses on being a first stage or early operations implant. That means that it's essentially built for those situations where you need something light, something that's less likely to be detected, just to get started on your operations. For example, just after that phishing email or initial compromise, you can drop Nimplant. The chance of being evasive is a bit higher, and you can use Nimplant to set up the later stages. So for example, if you want to switch to Cobalt Strike, you could load Cobalt Strike in memory using Nimplant. That's kind of the idea. So it being lightweight and evasive by default, which requires some configuration, of course. We will get into that as well. But if you want that lightweight implant to get started and drop the thicker implants as you go, that's essentially what Nimplant was designed for. Nimplant started as a side project. So essentially, first of all, I wanted to learn about the Nim programming language. That's already well over 2 years ago now that I released the first version. So that version was built in Nim. But yeah, after that, it basically grew. I wanted to touch upon more areas of offensive security development. So, for example, the building the GUI was very interesting as a sub project. And now for Black Hat 2024, I built a Rust implant as well to add to that. But we will get into the new features in just a bit. Nimplant is fully open source. It's MIT licensed. That means you can find it on GitHub, see everything, how it works, the core features, and you can use it as part of your own projects as well. If you happen to do so, please let me know because I'm always very interested to see how Nimplant is being used and of course how I can improve it. So if you have issues or feature requests or most preferably pull requests, then those are very, very welcome on the GitHub repository as well. So as I mentioned, there are already a lot of C2 frameworks out there. There's often criticism that people just keep publishing new command and control frameworks for seemingly no reason. For Nimplant, of course, that's no different. Nimplant was definitely not the first C2 framework out there, nor was it the last one. I still wanted to publish it. That has a couple of reasons, of course. So first of all, as I mentioned, it was for myself to learn, right? To build something first in Nim, then I added the Python server side, then the React frontend, and all the other components of the architecture that we will get into. I wanted to learn from building that, and of course share it to show essentially what I've built and to see how I can improve upon that. That's only one component, of course, because it is still considered malware. So then you could argue, why would you open source malware? Well, that has a whole other reason. In essence, I open source it to educate and inform both people in offensive security, so to show what can be done if you take the effort to build custom tools and not just take the tools that are already out there and have yeah, a lot of AV signatures, for example. I wanted to show how effective can it be if you build your own. That's one side of the story. And of course, it's also useful to show to defenders what happens if uh, people in offensive security uh, take the time to build their own tools, right? And to show certain techniques in Nim and now in Rust, how people in offensive security can apply them to get around defenses, with the ultimate goal, of course, being to improve upon these defenses. And I think personally that it's very important to give full transparency on the open source toolkit to show defenders what can be improved about defense, because in the end, people that are in offensive security, our goal is to improve defenses as well, right, and make the world a better place. Our goal is definitely not to just dump malware on the internet and get everyone infected with it. In the end, my rationale is to improve security. You may argue that, of course, in which case I'm very interested to hear your argument. Again, if you're at Black Hat 24, come find me at the booth and we can have a nice discussion about the topic, because I know it's a much debated one. But that's my rationale at least. And on top of that, I think because, of course, in the end, I'm publishing malware, I think it's very important to do so responsibly, meaning that the repository in its core is defanged a little bit. So I mentioned it's uh, meant to be evasive by default, but a lot of these evasive defaults that make it easy to get around defenses have been taken out for the public version, because I don't want people to just grab it without knowing what they essentially are doing and deploy it on client systems, or even worse, for cyber criminals to abuse it in, for example, ransomware attacks. So I took a lot of the dangerous features out of it, or it requires some tweaking and understanding what you're doing to get them back in. I try to give defenders early access to build rules and basically get informed about the techniques that are being used ahead of the release. And finally, there's also detection guidance provided by the same defenders in part, included in the repository and accompanying posts and so on, to hopefully make sure that if it is abused somewhere, that it's easier to catch in a timely manner. So in my mind, this whole topic makes it or this combination of factors makes it still a responsible act that improves transparency in the space of offensive security, and hopefully in the end improves defenses rather than causing harm. So that's enough about the why. Let's actually talk about Nimplant, what it is and how it works. On the screen here, you can see the basic architecture of the system. As you can see, it's fairly straightforward. There's a couple of components that are worth noting. So first of all, and let me try to grab a laser pointer here to guide you a little bit. First of all, what we have is of course the core, which is the implant. The classic part was the Nim implant. Now for Black Hat 2024, I added a fully functional Rust implant as well. It does essentially the same. So functionally, these two are very, very similar. And when you just use them, you wouldn't notice too much of a difference in how they work. But of course, at its core, it's completely rewritten. It's all native code, meaning that it's very interesting if you want to learn Nim or you want to learn Rust, or you want to compare how they perform against certain defenses. Then, of course, these are at its core completely different implants. Um, the Rust implant is a little bit more focused on operational security in the sense that it has more code that is related to handling the memory. So, for example, all the configuration files or configuration variables that are in the implant will be in the implant in plain text for a very, very short time. So there's a couple of more OPSEC features in the Rust implant that are very interesting. Don't have time to discuss them in this video, unfortunately, but reach out if you want to know more or find me at the Black Hat Arsenal booth this year. But the implants, as I mentioned in the core, they are the same. There's a couple of artifacts that you can generate based on the implants. So you have the straightforward executable, right? .exe, you can double click it, it works. Similarly, the .exe that deletes itself. This is a small trick that makes it easy to hide the artifact while it's still running. So you can double click it, it will run, it will disappear, but it will be in memory running. So it frustrates certain investigations to a degree. There's a DLL file that you can use for side loading, those types of attacks. It has a default entry point, but that's of course easy to configure. And finally, there's of course also the .bin format or the shellcode. Nimplant is not native shellcode. It's a reflective DLL. So essentially, it's the DLL being compiled and loaded into memory using the shellcode reflective DLL injection technique, which is already public. So that's not new. But the result is, of course, a blob of shellcode that you can inject into other processes or use in your packer, stuff like this to have more advanced payloads based on the implant. That's essentially it for the implant. What you can all do with the implant, we will get to in the demo in a bit. So let's move on to the server side. The server side's actually in its core, it's a Python server, which runs on well, whatever machine you want it to run. You can use it on the machine that you compile your implants on or completely separate. But it is essentially yeah, two servers that are running. One of them is the API server that keeps track of all the implants and manages their state and exposes that to you, the user. And of course, you have the listener server, which catches the implant communication, sends back the commands to the implant, and make sure that well your implants can actually do what you want them to do. Of course, the listener should be exposed because otherwise the implants cannot reach it. You need to take some OPSEC precautions when exposing it directly. There's more information in the repository, but that one should be exposed. The API server and the front end should never be exposed publicly. These should be behind some kind of jump server or based on a certain authentication flow. I've seen instances where these are exposed to the internet. That's very, very bad because that means that anyone can see what you're doing and potentially your client data as well. There's of course a database to support it and to make sure that if your server crashes for whatever reason or it exits, you can reconstruct the sessions based on the data that was there before. Finally, there's a front end as well. This is a web-based front end. You can use the console directly on the API server if you wanted to do so, or on the management server rather. So you can have a text-based console if you're into that. But mostly, I would recommend using the front end because it's just a nice GUI that has some additional features that make it easier to work with the Nimplant commands. This was built in Next.js, JavaScript framework. As I mentioned, mostly a learning project for me to build that front end from scratch. And it's web-based, so you can just access the web port and do your management stuff, which is also something we will see in the demo. For Black Hat 2024, as I mentioned, some exciting new features. Most of all, the Rust implant, the full rewrite of the Nim implant, functionally similar, but in its core, very, very different. So definitely have a look at the code if you're interested in that. And I also added a fully Dockerized setup, essentially meaning that you can do the compilation or the running of the server from within Docker, which saves you from installing all the dependencies that you need on your system and makes the whole workflow a lot easier as well. We will see this in the demo as well. So how to use it? I will briefly go over this in the demo. We will see how it actually works. But getting started is quite easy. Essentially, the only thing that you need to do is copy the config.toml example file and fill it in with the variables for your situation. Most notably, these variables are going to determine where your server listener is going to be. So for example, which domain you use for C2 communications. It's going to have some options for the implant as well. So for example, you can enable or disable dangerous features which are more likely to get detected. If you disable them, they will not be compiled at all, so they will not be in the artifact, which greatly reduces your chances of getting caught. Of course, it also reduces functionality a little bit. So all these kinds of features are in the configuration file. Once you have that configuration file ready, you can save it on your server and start compiling your artifacts. If you have Nim or Rust installed locally, you can just run the nimplant.py helper script to compile the artifacts. If you have Docker, I would recommend using Docker because that's the known good and supported state for compiling all the artifacts as well. Works for both Nim and Rust. And then once you have your artifacts, you can run the server. As mentioned, this doesn't have to be on the same machine. If you run them on different machines, there's a couple of things that you need to take into account, like the XOR key that's generated needs to be the same, and certain settings in the configuration.toml file need to be the same. Other than that, this can be completely separated as part of your offensive workflow. And of course, the server can also be run via Docker to avoid installing all the Python dependencies on your system yourself. And that's basically it. When the server is running and the artifacts are compiled, as you see on the screenshot, you can start delivering the artifacts and crossing your fingers that the implants will actually start beaconing back at some point. So usage is also hopefully self-explanatory to a degree. There's of course the famous help command, which shows you all commands and a brief explanation. You can also type help and then a specific command to get a more extensive explanation. As mentioned, if you want to use all commands, including process injection, beacon object file injection, inline execute assembly, these are all considered risky because they do some naughty stuff on the operating system. Then make sure that you compile it in risky mode, otherwise you will get a warning at the runtime that you cannot run these commands. And for some commands, like for example the execution of beacon object files, in the GUI, in the web front end, there's a modal that helps you basically select your arguments and have them in the right structure. Especially for beacon object files, this is quite useful because, of course, you need to define an array of arguments which is in a certain type that the beacon object file expects. So as you can see on the screenshot, if you just type the command, in this case inline execute without any arguments, you will get to see the modal where you can upload your beacon object file and choose all the arguments with nice drop downs. Choose the entry point, and then once you're happy with the arguments, you can just type execute, and it will make sure that the command is formatted in the right way. This GUI modal is available for certain commands like inline execute, execute assembly, shellcode injection, stuff like that, to just make the more complex commands, especially the ones that involve uploading files, a bit more easy. Other than that, I would recommend just installing it, playing with it on a test setup before you start your operations with it. See if it fits your use case, if everything works as expected. But hopefully, other than that, everything should be self-explanatory. So with that said, that's actually all I want to say about Nimplant in terms of design thoughts and the architecture. So I would say let me switch screens for a second and let's jump into the live demonstration. All right, so here we are in the demo area. First of all, let's have a look at the repository. As you can see, this is still my private variant of the repository because well, work is still in progress, and this is to be released at Black Hat 2024. So this is like a sneak preview of the dev environment. Even though this is essentially the mirror of what will be public during Black Hat. So as you can see, the repository contains a extensive README. This README essentially has all the instructions that we just quickly went over, and show you what to configure, what every setting means, and also how to compile and also use Nimplant in your operations. So everything should be fairly straightforward, but again, if you have any trouble, make sure to go over the README and check if everything is configured as expected. As well as if you have any issues that you want to raise, make sure that you go through the troubleshooting steps. For example, try to compile in Docker before you raise the issue, which saves me some work on issues that can be prevented on the user side. So let's go over the full flow of how to set up and use Nimplant in your operations. As I mentioned, the first step is essentially the config.toml file. So let's see if I can make this a little bit bigger. There we go. As you can see, the configuration file is fairly straightforward. There's essentially three categories. So one is server, which is essentially the management server, or the configuration of the API server. Then you have the listener settings, which determine where your implants will call back to, where they live on the internet, what your domain or your redirector domain is going to be. And finally, you have the Nimplant section, which actually determines the settings for the implant itself. So let's quickly go over them. As you can see, there's comments for every setting as well. For the server settings, I'm just going to leave them at the defaults because well, it's going to listen on localhost. If you set this to 0000, that means it will listen on all interfaces, which is fairly dangerous because the management server itself should only be accessed by you or your fellow operators. So I would recommend keeping this on local, and if you want to expose it, use something like SSH tunneling to access the port and not just expose it on the interface itself. Default port is 31337, very lead, so we'll leave that as it is as well. For the listener, I'm using a local testing setup, so I'm going to keep it at HTTP and localhost port 80 as well. If you want to use HTTPS, for example, with something like Let's Encrypt, you can do so. Just specify the certificate and key path here, and Nimplant will gladly use them to spin up a server with SSL enabled. The host name is going to be important in production environments as well, because this essentially determines where the implant will call back to. If there's no host name, it will use a combination of the IP address and port. So in my case, it will just use the localhost IP, but in practice, you want Nimplant to not call to a role IP, rather a actual host on the internet. This can be a redirector IP. So if you have a redirector in front of Nimplant, which is actually recommended, then you would put the host name of your redirector here and just configure the Nimplant to listen on all interfaces or the interface where the redirector can reach out to. Then you have the URI paths. This essentially determines where Nimplant is going to call back to for each of the different tasks that it has. By default, it uses /register/task result. This can, of course, easily be fingerprinted, so make sure to change that to something sensible in the context of your command and control setup, where you hopefully can blend in a little bit with legitimate looking traffic. Then for the implant settings, we have a risky mode. I mentioned this already. This essentially determines that whether or not you can use dangerous commands. Would recommend setting it to true because it enables all the functionality. However, as mentioned, in very high profile scenarios where you just need to perform basic reconnaissance, for example, or just those very early access operations, and staying undetected is really the main driver, then definitely set risky mode to false, because it will make the implant much more slim, much harder to detect, and also protect you from making mistakes with dangerous commands that could get you detected. There's also the sleep mask setting. This determines if, when set to false, an implant will just have a normal sleep call, which means that all the memory of the code, essentially, of Nimplant will stay in memory. This is up until now, an Nimplant has been released for 2 years. It's not too much of an issue because there's not many memory fingerprints for Nimplant that are used by the big detection providers. However, again, if you are in these high OPSEC scenarios where this memory needs to be protected at sleep time, you can set it to true to encrypt the memory before going to sleep, and use the echo technique for the Nim implant to cue timers and then wake up again before the next instructions come in, and rinse and repeat. So this essentially protects your memory at rest. But again, I would recommend keeping it at false unless you really need it. Default sleep time and jitter, these are set quite low by default. For production, I would turn them up quite a bit. However, this is something that you can modify at runtime as well. So it's just this starting check-in before you had your first operations. It will check in with the sleep time and jitter. Kill date, self-explanatory. If this date passes, then Nimplant will kill itself, or when it boots after this date, it will immediately terminate. This is, of course, very useful as a guardrail during red team operations, where you don't want any malicious code to be running after your engagement ends. Of course, you should always take care to clean up any scheduled task or whatever you have running still. But this makes sure that there's no risk of Nimplant calling back to someone that took over your C2 domain or something. And then we have the user agent that Nimplant uses to connect. This is used as one of the steps of the verification between the server and the client. If a unexpected user agent comes in, the server behaves differently. So make sure to set this to something that both looks very legitimate, blends in as much as possible, but also is not the most used user agent, because that could mean that forensic investigators, for example, that use that user agent can get some more information from the C2 server. This is not a huge problem because there's many more steps of identification, including the pre-shared key for the first check-in. But still recommended to keep this as a sensible default. So again, my setting is pretty vanilla. There's a couple of scenarios where you would need to configure more complex settings with the host name and so on. But for now, we're not gonna get into that. So then let's switch to my terminal. As mentioned, Nimplant has a helper script, nimplant.py. It has a couple of options for a compilation, running the server, or cleaning any server artifacts that are left. And obviously, when we want to run Nimplant, we need to first have an artifact. So in that case, we would use Nimplant compile. As you can see, there's essentially two positional options here. The first one is which artifact you want. These are the ones that we discussed in the slides. You can also choose all to compile all of them. And then there's the actual implant type that you want. Up until now, this was only Nim and Nim debug. And new for Black Hat 2024 is of course the Rust implant, as we discussed before. The debug mode is useful if you're testing something and you want to see what the implant is receiving and saying. It will pop a console window which basically has all the debug messages in it. So definitely don't use it in production. In production, stick to the production payloads, which are a lot smaller, and also ensure that they run in the background without any footprint that the user could notice. So for now, let's compile a Nim executable, for example. In that case, we just say compile exe nim, and it will get started. In this case, I'm not using Docker, by the way, because I'm on my Windows test setup. But if you're using Docker, the syntax is exactly the same. Let's also, just for fun, compile the Rust executable. Works in the same way. Again, the helper script takes care of all the tool chains for you and the stuff that you need to get the most out of your OPSEC, for example. So it will take care of all of that for you. Compiling Rust is unfortunately a little bit slower, but the more you compile artifacts, the quicker it gets, luckily, due to all the caching that Rust does. Cool. So now we have the artifacts in place. The next thing we can do is essentially just start the server. Again, I have all the Python dependencies here, so I can just run it on my host. This is also supported to do through Docker. If you use Docker for this, make sure that you, of course, port forward the right ports on your Docker machine, because otherwise you won't be able to reach this IP address. So this will expose our web interface. As mentioned, there's the GUI as well. Right now we cannot do anything because there's no implant. Sorry, the command line interface. But the GUI is mostly recommended for controlling all your implants. As you can see, the interface is fairly simple. There's not too much to see here. We can get information about the server that's running. We can see the same console output that we see in our actual console. We can engage with all the downloads that we have, which we don't because we don't have any implants running yet. And of course, we can interact with the Nimplants that call back. So let's actually start an implant to get a callback and interact with this implant. As was listed when we compiled our artifacts, they are either in the client/bin folder for the Nim artifact and the client rs bin folder for the Rust artifact. Since the Rust artifact is new for Black Hat 2024, let's use that one. As you can see, when I double click it, we immediately get the callback here. So this is the moment we can start engaging with our implant. Again, we have the same information here, implant information. If you want to kill an implant, you can do it in this view as well. But primarily we have the console here, and the Nimplant console, as opposed to the server console, is actually the interactive console. That means that we can type our commands here. It has a nice autocomplete feature to help you find the commands. And of course, when we type help, we will get information from the server that shows all the commands that are available to us. Again, if we type help and a specific command, we will get the help information, the more detailed information for this specific command. So in this case, I get all the information back from execute assembly. We can get the properties. It shows that it's a GUI command, which means that it has a modal that we can use. We'll demonstrate that in just a bit. And we will also get an extensive explanation of how the command is implemented, how it works, some obsec guidance even, and which arguments it takes from the command line. So as I mentioned, commands that are listed as GUI, those ones will have a modal that we can use. This is especially useful for commands that take a file. For example, if we want to upload a file to the victim machine, this has a GUI. So for example, we can type upload without any commands to see the arguments that we have and get a nice file upload prompt, which will take care of sending the file to the server, and then after that sending the file to Nimplant. So it saves you some hassle transferring files. And of course, there's the other arguments. So let's actually try that with execute assembly. We use it without any arguments to get the modal. Again, there's some guidance here. I have Rubius pre-compiled here on my system, which is a nice assembly, of course, to demonstrate this feature. Execute assembly is considered a risky command, by the way, so if you compile it in non-risky mode, you will get an error trying to run it. So we're using Rubius as commands. Let's just use triage to get information about tickets on the system. It's a non-domain joined system, so this will not be very interesting, but hopefully we can see it work at least. Then there's two options to patch MC and block ETW. These are used for the inline execute assembly as we're using here, and also for the in-memory PowerShell commands. If you want to patch them, you can have them enabled. I will just keep them enabled here. They will only patch once, so if memory is already patched, it won't do it again. So let's run that. Again, if we accept the modal, it will take care of the whole command line for us. So you can see that the MC and ETW flags are here. File is uploaded to the server itself. So it's moved to a specific folder on the server, and then sent encrypted to Nimplant along with our arguments. So as mentioned, our output here is not very interesting, but that demonstrates how the modal works. I also mentioned the inline execute command, which is the BOF execution, which has arguably the most complex command line arguments. So if you don't want to remember all of them, just use the modal. In this case, let's use the dir BOF from the trusted sec BOFs, which has the go entry point. Usually it's go, but if you have another entry point, you can change it here. And here is the nice feature, because you can just add as many arguments as you want and choose the type without thinking about which types are available, how to provide them on the command line, stuff like that. I think dir takes a directory to enumerate, and it also takes an optional integer to specify whether or not to enumerate recursively. So in this case, let's enumerate the public directory recursively. That's all the arguments we will provide. There's other types, of course, binary if you want to do shellcode injection via BOFs, for example, a very nice way to make an implant more extensible, or the other types for wide string or short numbers. I think this should work, so let's send it over. Again, the dir BOF file is sent to the server, and then it actually executes it in memory with the arguments. You can see the syntax here. This is the directory provided as a string, and then the number provided as an int. But again, using the modal is much nicer. And we can see that it works. Of course, this is a bit of a contrived example, because we can just use the ls command as well to list directories natively in Nimplant. But of course, with BOFs, you can just add any functionality that you want. That's probably as much as I'm gonna demonstrate of the Nimplant commands. Of course, there's much more. A lot of enumeration commands that use WMI or the Windows API to get system information, which is very important for a first stage implant. There's commands to affect the behavior of an implant, like the sleep time. There's basic situational awareness commands like ls and cd clearly. There's just much more. So I would recommend reading the README and the help pages and just playing around on your own system with Nimplant to discover what the capabilities are. I would say it's not a feature parity with the leading C2 frameworks, and again, that's by design, right? Because it's supposed to be a flexible first stage implant rather than a fully featured, very heavy implant that's also easier to detect. So this concludes the video demo of Nimplant. Thank you very much for watching until the end. If you have any questions, again, reach out on Twitter, find me on GitHub, or if you're at the Black Hat 2024, come find me there at the booth. Thank you so much, and have a great rest of your day.